So I work in the matrix lab, which is led by Dr. Fani Motamari. So I'll be discussing on the need for real space finite element based DFT calculations. I'll be motivating this with applications to energy material research as a use case scenario. So from the seminal work of Walter Kohn, which was published in 1964, DFT has found applications in wide varieties of areas. So from semiconductor research, biomedical, drug discovery, and in energy storage materials. So the high throughput calculations, which can be used directly in energy material researches, we could use it for computing properties like formation energy of electrolyte, the thermal and chemical stability of electrolytes. We could compute the energy barriers at the electrolyte interface or the activation energy for ion migration. You can compute the ionic diffusivity by performing ab initio molecular dynamic simulations, and we can compute the electrode potential. But however, there are certain problems that we could not run through these high throughput calculations because we require certain boundary conditions. So there's a need for large scale DFT simulations with arbitrary boundary conditions. For example, we deal with something of this, of the non-stoichiometric surface energy. So here, so by non-stoichiometric surface energies, when I need to compute the surface energies of systems where the surface of the stoichiometry of the surface is different from that of the bulk. So we generally end up with systems which have non-charge neutral. So for this, typically in the current periodic simulation codes, what people do is they use either compensatory charge or they introduce vacancies with the opposite charge, which changes the nature of the system. So if we could treat this with imposing some kind of semi-periodic boundary conditions, we should be able to solve this. One of the goals of my research is to understand the solid electrolyte interface in the presence of an electric field. So this too in the periodic boundary codes will create some kind of spurious potential. So large nanoparticles, nanoclusters are of critical area of research for hydrogen storage. So here we would be dealing with systems of close to thousands of atoms. And if we were to use periodic codes here, we would have to create a large vacuum, which will become computationally inefficient. So there is therefore a need to move from the conventional state-of-the-art DFT codes, which are mostly plane wave-based codes or the atomic orbital-based codes. These plane wave-based codes restrict the simulation domains to be periodic, and the atomic orbital-based codes do not lack a systematically convergent basis set or become ill conditions. You cannot treat large systems. Also, in the exascale era of today, we would like to take advantage of the heterogeneous CPU-GPU architectures that are available. So, in the three problems which I am interested in, I would require to have some kind of basis that gives me an extremely scalable that can handle periodic, semi-periodic, and non-periodic conditions, and that can compute for about 10,000 atoms. So. One such basis set which we are resorting to is the finite element basis. So the finite element basis uses Lagrange polynomials as its basis set, where the values of the function can be found at the grid points and its gradients can be computed in each element. So consider a 1D domain omega, which we could discretize it as omega 1 to omega n. And if we know the true solution, let's say it's u of r, we could find the approximate solution as the linear combinations of these Lagrange polynomials. So by using the finite element basis, we get a lot of advantages, which is what we are interested in. So if you notice here, the value of the basis set is non-zero only in the grid points or in elements surrounding the grid point. So this gives us a compact subboard. So when you're dealing with large scale multiprocessor, communication cost starts coming down, and we are required to have a refined mesh only near the atom domain. Because only here there'll be a lot of perturbations to the Kohn wave functions. So we could gradually coarsen our mesh all the way towards the end of the domain, and we could save on computational cost. Since we're using a polynomial basis, we end up with a convergent basis set, and this also allows us to naturally set up any arbitrary boundary conditions. So the real space finite element formulation which was published in 2019 can be found here. And if we were to convert it into the finite element discretization, we would have to solve the Kohn wave functions and the electrostatic potential on the mesh, which comes out to be a generalized eigenvalue problem. But by choosing certain computational efficiency techniques, we could convert it into a standard eigenvalue problem, where we are interested to solve only for the smallest n eigenstates, where we can use Davidson algorithm or the Jacobi-Davidson algorithm and get our results. So DFT-FE, which was released first in 2019, and in the last week or so, we had released the version 1.0 in early week of March, which gives us the real space finite element based DFT formulation, which I'm looking for. So DFT-FE uses the adaptive capabilities of finite elements. It uses the eigensolver as the Chebyshev filtering method, and it treats forces and stress in uniform framework called the configurational force approach. So what we get with the DFT-FE approach is that we get a unified framework for dealing with all electron and pseudo-potential calculations. We get to impose fully periodic, semi-periodic, and fully non-periodic boundary conditions. And we get to solve for systems ranging from 1 lakh electrons. So DFT-FE is also extremely scalable. So we have shown scalability, perfect scalability for up to 190,000 CPUs and 4,000 GPUs. So this should be the area which I will be working on. This should be the basis. This should be the fundamental framework which I will be developing my implementations to solve the problems I have in mind. So when DFT-FE was first launched, it was released in 2019. There was an extensive benchmarking and to compute ground state properties and ground state forces. But for my research, which is towards energy storage materials, I had done benchmarking for formation energy, diffusivity, and activation energy. So we got a good, we compared our results with quantum espresso, which is the plane wave code, and with experiments, and we found that we have a small deviation of only 2%. To compute diffusivity and activation energy, I had implemented the AIMD framework and the NEB framework. So the AIMD framework calls the DFT solver at every time step to compute the energies and forces. And we have implemented the Nosey-Hoover change and the CSVR thermostat to get our NVT-on-soul properties. The NEB framework is implemented in DFT-FE using the global vector, where we try to optimize for a global vector of forces. We assemble the forces, which I call here as the FNEB. Is basically the perpendicular force and a force that comes from perpendicular of the tangent connecting two reaction coordinate configurations, and the force parallel along the tangent, which is coming from the spring force, which is an imaginary spring that we connect. So the DFT-FE computes the forces in a loop, and the loop ends once the F perpendicular is close to 0 or once we've reached the minimum energy path, which gives us from which we can compute the activation energy. So we have done benchmarking of lithium oxide, and we will be taking this for other electrolyte materials like lithium lanthanum zirconium oxide and maybe LGPS. So we see the diffusivity had similar trends as quantum espresso, and our activation energy are close. We are still working on, we are doing this calculation for further systems also. So apart from this, we have integrated the projected finite element orbital population analysis. So there are scenarios wherein we are interested in understanding the nature of bonds between two atoms of a particular system. In that case, what we do is once the DFT-FE completes its calculations of the Kohn-Sham wave functions on the finite element basis, we orthogonally project it onto the atom-centered atomic orbital basis. So once we have the details on atomic orbital basis, we compute two properties, the orbital overlap matrix and the projected Hamiltonian matrix. So with this, if we are interested in to understand the bonding nature between a particular atom at R and R prime, we compute this using the values of the projected Hamiltonian and the coefficients of the projected wave functions. So we have done a benchmarking with a few systems of both periodic, non-periodic, and with spin, without spin, but whole dealing with only the gamma band calculations. And I've just put up the results for carbon diamond, which is a periodic system. So my work is to understand, to improve the modeling capability of DFT for understanding complex engineering energy storage problems. So towards it, which we have first benchmark the existing DFT-FE framework for ion migration, formation energy, diffusivity, and bond strengths. We plan to extend this formulation to deal with non-charged neutral surfaces, presence of an external electric field. And currently we are somewhere over here. We are trying to implement both of them, and we'll be releasing 2 papers for this. And the current DFT-FE formulation deals only with the GGA exchange correlation and with norm-conserved pseudo-potential. But we would be dealing with large systems we will be considering large systems, and we will be dealing with long time scales. So we will have to develop more computationally efficient frameworks. So we'll be reformulating the DFT-FE framework with the projected augmented wave pseudo potentials, and we'll be implementing even the scan and or scan plus U exchange correlation. And since we'll be dealing with MD simulations of very long time steps of very long time scales, we would try to accelerate our MD simulation by using the extended Lagrange BOMD formulation. And so the goal is to understand the cyclability and the performance of solid lithium electrolyte batteries. So these will deal with very long, more than what we could do, more than picoseconds and nanoseconds of simulation. We'll have to do cyclability and studies. So on the systems level, we will be trying to deploy a graph neural network based machine learning framework, training with the data of DFT-FE, which we have generated. So our group at Matrix Lab not only work towards energy storage materials, they have a wide variety of problems. So our group is also working to re-implement and reformulate the DFT-FE framework to model non-local van der Waals functionals in DFT-FE framework. We're trying to implement the spin orbit coupling also here. And we're trying to have a hybrid DFT plus GNN based framework for accelerating our ab initio simulations. So I'd like to thank our collaborators at IISc and our funding agencies. So this attached a few.
So I have a question regarding the grid construction.
Okay.
You said you can use a hierarchical grid, right?
We can do it for adaptive mesh, yeah.
Yeah. So when you do AMD and as the atoms move,
yeah.
So the grid moves along with.
So we have a free floating charge domain. So the grid maybe we'll reconstruct the grid maybe after 10 or 15 time steps, depending on what we consider. We have an internal parameter that can decide whether to remesh it or not.
So it's done automatically.
Yeah, and it's mostly in AMD. We train currently we have is a uniform mesh, so that we don't need to worry about remeshing and again. But we could try if we're looking at a trade-off between computational efficiency and this thing. We'll have to look at other ideas.
Okay, all right. Thanks.
Sorry, next question.
So there is a software called JPO, and they have implemented, I think, finite difference method there. And you are saying here, I think, finite element, right? So have you looked at that software?
So the problem with finite difference method is they don't give a convergent basis. They don't have a convergent basis.
And that is very.
Can you hear me? Yeah. So yeah, finite difference bases have been around in DFT, I think 1993. So the advantage which finite elements will provide is, first of all, it can handle adaptive meshes, which allows a better computational efficiency. And also you will have a better scalability, because usually to get chemical accuracies which are required in finite differences, you usually have to have very high order stencils, and which affects the scalability. So finite elements have shown to be much better scalable than finite elements, finite differences. And when you come to heterogeneous architectures, at least when you're talking about today's GPU, CPU architectures, at least we did not see papers in finite difference implementations which can actually give a very good GPU speed up. We have seen papers where implementation of plane waves in GPUs, but in finite differences we have not seen. Whereas we have observed actually around 20x CPU GPU speed up. So which means we can really take advantage of heterogeneous architectures better in finite elements than finite differences. So these are the advantages which we think would potentially be leveraged with finite element basis.
Any other questions, comments? What is the effective scaling that you achieve?
So we get an n-cube scaling, which is very delayed. So for about 20,000 atoms, we are able to get it into the quadratic regime. 20,000 electrons.
What is the largest system you have tried?
So which involved actually a 10,000 atoms magnesium dislocation system, which had around 10 valence electrons. So I think it would be better to measure the size of the system in terms of electrons. So the 100,000 electrons largest we studied actually. So.
Is your code still in the developmental stage? Already?
Yeah, so we have released recently, last week, in fact, GPU, CPU architecture based DFT-FE, which handles currently norm conserving pseudopotentials and GG exchange correlations. So it's already released. It's an open source code actually right now. Yeah.
Great. Thank you very much.